Okay, I'm Prater. I'm a staff engineer at Shopify, and this is what peak performance looks like. And you may not like it, but I'm only kidding about that part. This is a talk about performance tuning, but it doesn't include a lot of math. If you've done an engineering interview in the last 5 years, someone has probably asked you to write an algorithm like this one, and then to tell them the big O complexity of it. But if you've held a job as a software engineer in the last 5 years, you have probably never done this at work. Because in real life, your algorithms aren't really this compressed. Your algorithm is probably scattered over a half dozen methods in three classes, and trying to calculate the big O by hand seems like a waste of time. And you'd probably be right. Because in real life, in the sort of system that we deal with every day, there are 3 big O numbers that you need to worry about. There's O1, ON, and O no. I mean, I'm being a little bit flippant, but roughly categorizing your runtime into these 3 buckets and then figuring out why they're there can help you verify that you're getting the most performance out of your program. And it's easy to make those categories. It doesn't require a ton of complicated math or even really reasoning about the algorithm in your head. But how do we do that? How do we categorize runtimes without the tricks like, oh, we look for nested loops when those tricks aren't available for us? It's hard to recognize a nested loop when the nested loop is in a whole different application or 10 frames up the stack. But what we can do is look at pictures. So OpenTelemetry is a collection of tools, APIs, and SDKs that can be used to instrument, generate, collect, and export telemetry data like metrics, logs, and traces to help you analyze your software's performance and behavior. And these tools can give us traces and graphs of distributed algorithms. And learning to recognize the performance characteristics by looking at these graphs gives us a shortcut to understanding the complexity of our system. We're not going to get too much into how to instrument your code using OpenTelemetry. I've got like a few tricks that I'm going to show, but there are a lot better tutorials and ways of doing that. This is about once your code is instrumented, how do you make sense of all of the data that you now have at your fingertips? This is about how to recognize and eliminate performance problems, acquire a reputation as a wizard, and summon an army of cats to assist in your nefarious plans. I know I just said we weren't going to get into instrumenting your code, but I do want to make like a little cautionary note here. Performance can't be calculated, only measured, which is a great quote from a guy I know on the internet. And it follows that you can really only improve the performance that you measure. And it's important to understand that how you instrument your code can have a big impact on the problems that you can visualize. And today we're going to be looking at flame graphs and distributed tracing timelines from Jaeger, which are generated by code where I used TracePoint or clever metaprogramming to instrument every single method call. And I would not do that in real life because you will get absolutely flooded with data that's not really actionable. But I did this mostly so that I could show the general principle of looking at the graph shapes. In your everyday work, you're not necessarily going to be looking at complex single method calls, but rather at invisible complexity that's spread over multiple call sites and even multiple programs. We can get into the specifics now. So fundamentally, there are 2 things your program can do that make it slow. There's too much something or too much nothing. And what that means is that when your program is waiting on something, either itself to finish what it's doing or some other program to finish what it's doing, that's when things get slow. Like a common frame that you'll hear when people talk about performance is that you're IO bound or CPU bound, but I think it's more useful when you talk about like, what do I have to do to fix it perspective to think about what your program is waiting on. And we're going to talk about waiting for something else to happen, slowness first, because this is the kind that you are most likely to encounter in a modern application, where you're often waiting on collaborating programs to return information that you need. Waiting for things is what happens when your beautiful software just smashes headfirst into the wall of reality. Like doing things on the CPU takes time, reading files from the disk takes time, talking to that shitty API you hate, that takes time. All of these things are impacts of the physical world on your program. And oftentimes the slowness is kind of unavoidable. I mean, what can you do about an API that takes 3 seconds to respond to every call? So this is our first flame graph, and what do we think that this shows? And this is the code that produces that flame graph. Any ideas from the audience? No? Okay. All right. So this is a picture of an extremely common performance problem in Rails, the n+1 query. And this happens when you don't eager load a one-to-many association. And iterating the association requires you to perform multiple database queries to fetch each object, which is normally one at a time, from the database. And the solution to this is pretty well known, which is to eager load your associations. But why is an n+1 query slow? Every row out of the database has to be converted into a Ruby object and then pushed onto the association. What does it matter if you retrieve them one at a time and push them all onto the association, or if you retrieve them all at once and push them one at a time onto the association? For one thing, a fundamental truth of computers is that closer is faster. So in this case, multiple trips over the network, even if it's just to your own computer, take more time than multiple iterations by the CPU. And so our first rule of performance is closer is better. When you can, move things closer to you before you operate on them, and use the CPU rather than the network or the disk. And here is a picture of a method with a network delay. So here's the thing about waiting on I/O. That is an inevitability. Every time you read from a data store that's not a local variable, every time you make an API call, anytime your program makes a call to an external collaborator like a database, every time you're going to wind up waiting on I/O. And each one of these little stair steps here represents a sequential operation that's waiting on the prior operation to finish. And we can use our flame graph of the same program to find that a large percentage of the time is spent in method named things like I/O wait. And this is probably the most common type of performance bottleneck in distributed systems. And so systems like Jaeger and Tempo will excel at showing you this problem. The stair step look, that's a tell. And another telltale sign of waiting on I/O is suspiciously round numbers. If your call always takes exactly 30 seconds or almost exactly 1,000 milliseconds, start looking for a timeout or a sleep or something. And the last indication of network or device delays is differences in how long something takes. This call doesn't have as much variance as some of the other ones, but if you can correlate a random slowdown with a spike in network or disk traffic, it's likely that your problem is waiting on I/O. And this leads to our second rule of performance: don't wait around. But what does that mean? Well, this is the output of the program that produced the previous traces. So it retrieves cats from the database and then fetches pictures of them from the cat API. And what don't wait around means is that while this program is waiting for your cat image to descend from wherever cat images come from, there's plenty of other things that they can be doing. It's taking us about 2 seconds to retrieve pictures of these 10 cats. And this is the source code of our program. A lot of times, our programs are organized, like this one is, to operate in a way that makes sense to us, even if it's not absolutely the most efficient use of time. That's fine, that's good, because most programs are read far more often than they're written. But when you see a graph that looks like this, with the stair steps, it's time to ask yourself if everything over here really needs to wait around for everything over there to finish. Maybe this call has a minimum amount of latency. It's just inevitable. The network is slow, the database, is overloaded. Are we sure there's nothing we can be doing while we're waiting around? We're going to take a real quick detour into JavaScript land to talk about parallelism, and I'm going to shout out JavaScript here for the really elegant solution in waiting around for I/O in the native support for promises. Depending on how long you've been writing JavaScript, you might realize that those promises, await and async, are syntactic sugar over .then. And if you're as old as I am, you might realize that it's semantically equivalent to these kinds of callbacks. And in the last example, it's clear that plot destruction actually gets called before we pet the kitty. We don't need to wait around for summon cat to finish before we start plotting destruction, because we don't need the cat to plot destruction, even if he wants to participate. So while Ruby's concurrency primitives aren't quite as convenient as JavaScript, we can see that we don't actually need to wait, and there's no reason for it to wait to run that fetch. There are several approaches to achieving this type of concurrency in Ruby. Here we've got an implementation of promises from concurrent Ruby. We could do separate processes, or if you're particularly masochistic, there's the new hotness ractors. But the insight here is one of not waiting around and doing all the sequential things sequentially. All right, so not waiting on those cat pictures brought us about 100% speed up, and we can now do it in 1 second. That's not too bad. Unfortunately, my little trace point trick doesn't really work with multiple threads, so you'll just have to trust me that it did, in fact, run in parallel. All right, so we've got our solution. This is our solution. This is unfortunately not our solution. All right, imagine that we had 100 cats. And our job is to say each cat's true name and then pet it for 10 seconds, thus binding it to us. Each cat's true name takes 2 seconds to say, and each cat takes 10 seconds to pet. So 12 seconds times 100 cats tells us that it will take us approximately 1,200 seconds to summon and bind all of these cats, if we do them one by one sequentially. But I got 2 hands, and I can pet 2 cats at once, so that time is going to drop to 600 seconds. And since each cat can be petted and summoned independently, petting all the cats is called trivially parallelizable. And that's not to say that petting and summoning a cat is trivial, but that you don't need to change the algorithm that you're using in order to parallelize it. And since we're already summoning all these cats, and we're clearly using magic to do so, let's just sprout a bunch of extra arms so we can pet all the cats at once. So we're going to pet 100 cats and get it down to 12 seconds. Well, if 12 seconds for an army of cats is great, 6 seconds is better, let's sprout 200 arms. But wait, that is still 12 seconds. And this is called Amdahl's law. And the performance of the program is limited by its sequential part. Because each cat has to be summoned before it is petted and must be petted for 10 seconds, it's not possible to make the algorithm faster than that. This is Amdahl's law restated. The fastest you can go is the time it takes to do one thing. If you remember your big O math, you might remember that we can eliminate constants. And this means even though it takes 12 seconds to summon and pet the cat, this is actually considered an O1 operation because it always takes 12 seconds. So in OpenTelemetry, you can recognize O1 operations, roughly speaking, by seeing that it always takes the same amount of time. So O1 is called constant time for this reason. Here's some constant time things. Forget to hit the button. All right. So most interesting programs don't deal with a single object and a single operation. And if they do, they probably don't need a lot of performance tuning. Instead, they deal with a collection of objects. And remember that for every cat, we have to both summon it and pet it. And there's no way around it. This takes a predictable amount of time, and we have to do this method once for every cat that we want. Ruby calls this method map, or each, and you probably use it every single day. More cats takes more petting and more summoning. Well, this type of algorithm is called ON, or linear time. And I think you can see the line. It's pretty easy to see why. It makes a line. A lot of times, this is where you'll notice that things are slow. If you don't need to do operations on the actual collection of cats, then this is probably where you're going to start. Does this linear operation hide additional linear operations, or is it the smallest unit of work possible? Maybe it's parallelizable. Sometimes all you want to do is summon and pet the cats, but sometimes you need to organize them into neatly stacked piles of cats, and for that we'll need to sort the cats by size. When doing operation on the entire collection of cats, like sorting, averaging, or bucketing, is where algorithmic complexity comes into play, and in fact that leads to rule 4. Doing something with everything is complicated. For most of us, the type of problems that result in algorithmic complexity will be in this category. If you have a list of stuff and you need to know some facts about the list and not about the individual stuff in the list, then this is even true when it's not obvious. Like graph traversal problems, like how do I get from point A to point B, or what are the dependencies of this gem, are answers to questions about the group, not about the individual element. Take one away one of the elements, and the answer might change. Another example is retrieving one element from a group, a question about the group. Where is that element in the group? Doing something to everything, ON is probably your target runtime. Doing something with everything, it depends, but it might be more than ON. Need to get one thing out of several? Hopefully you'll be able to do better than ON, but luckily for us, that sort of operation is kind of localized most of the time, so we're not really going to get into that. But the canonical example of doing something with everything is going to be sorting. And let's start with a sort algorithm that we would never do. Let's take all of our cats, arrange them in all possible orders, and pick the ones where they're sorted. Sometimes they call this kind of thing a BOGO sort because you have accidentally or on purpose used the worst performing algorithm you can imagine. So this is an oh shit moment. This is an oh shit algorithm. This is factorial time. And because we know that there are n factorial permutations of n cats, I have about 30 cats in the database that I'm working with, and 30 factorial is 2.32 times 10 to the 32nd, which is a lot of zeros and a very large number. The far left of this, by the way, says 40 seconds, and this is sorting 7 cats. You probably can't really see the spike on the far right side of this flame graph, but this long shelf with a narrow spike way up there, that's the tell shape of a flame graph for a factorial algorithm. And in fact, full disclosure, this algorithm is so slow that I can't actually sort all the cats. If I do more than 10, it takes so long to run and it generates so many traces that it crashed the container that OpenTelemetry was running in. So if you find yourself looking at something like this, you done messed up. So unlike weighting or O1 constant operations, the hazard of this kind of complexity is not that it takes a long time, but that it grows so quickly with inputs. Like part of the truth of big O notation is that for small values of n, it's probably not a big deal if your algorithm is factorial. The permutations of an array of 1, 2, and 3, that's only 6 iterations. The permutations of an array of 1, 2, 3, 4 is 24, and it grows faster and faster the more items are in your array, and it gets out of control really quickly. So if you see this shape, probably want to try again. So here's the next one we're going to try. This is a selection sort, and it works by having 2 arrays, repeatedly finding the smallest element in the unsorted array, and then putting it into this sorted array. So I do want to say that I am no longer using like the trace point on every method. I am just annotating the trace calls here. And also that I'm implementing using this with recursion and without using loops. And the reason for that is because OpenTelemetry doesn't instrument loops unless you do it by hand. And I only want to instrument the important bits of the code and also to show you the shape of the performance graph. Like, there's not going to be a whole lot of moments in your career when the problem at hand is the need to summon an army of cats. But there will be a lot where performance programs that would be visible if they were loops in a single method are hidden across multiple methods and maybe even multiple servers. When we can learn to pattern recognize on these performance graphs, we don't need to reason about how many nested loops there are in our code, because we can just recognize the problem visually. So if factorial sections of your program are like an oh shit moment, polynomial time, like the selection sort, is only slightly less worrisome and way more common. So like a sawtooth pattern like this, you can kind of see it up at the top, marks this runtime, and its hallmark is like nested loops, even if they're hidden between multiple methods. So the amount of time spent in a polynomial algorithm grows polynomially. So adding a few extra cats to your hordes of feline servants quickly results in you running out of litter and overrunning the cat food budget. But it's still like so much faster than factorial. This takes 4 milliseconds and is able to sort 30 cats. When you look at a flame graph and you see this sawtooth pattern where all of the peaks are the same height, that's what a polynomial time algorithm looks like in a flame graph. So also another quick sort of disclaimer, OpenTelemetry visualizers all have like a different concept of what a graph should look like. So in the same way that like measuring is a decision, visualizing is a decision. And when we look at Jaeger traces, which are the blue ones, we're really focused on finding opportunities to parallelize. And then when we look at flame graphs like this, we're focused primarily on computational complexity. So every APM is going to have a different set of graphs, and they're all going to show largely the same thing, though, which is predictable shapes based on those certain runtimes. So this is our polynomial time sort. We can see that it does 498 iterations to sort 30 cats. I bet we can do better. So this is a recursive merge sort of a collection of cats, which is sort of a little bit complicated to go into exactly how it works, but it's reliably an n log n complexity. And in a lot of cases, sorting included, this is the best that you can reliably do. Like certain operations just require you to go over the list of object multiple times. And when viewed in a trace, a logarithmic algorithm will look, or a linear arithmetic algorithm will look like an upside down triangle. And if you arrive at an algorithm like this, it's pretty likely that you got the best one, but it never hurts to Google a little bit. Because despite what tech reviews would have you think, it's extremely difficult to come up with quicksort or Trajan's algorithm from first principles. I'm not gonna tell you it's not important to know those things, but realistically, you're not gonna be inventing novel quasi-linear algorithms on the daily. So these in-log-in runtimes are marked by these peaks that decrease in height. And what that means is that for every iteration that it goes through the loop, it has to do a few fewer iterations on the next loop through. In this case, merge sort takes about 1.2 milliseconds and sorts 30 cats. So it's about 3 times as fast as in squared. And the nice part about these kinds of runtimes is that they grow basically linearly the more elements you add. And in fact, in-log-in is sometimes called quasi-linear or linear-rhythmic because it's a little slower than linear. So we learned that summoning and petting cats is parallelizable, but what about those kinds of operations? What about sorting them or adding up the total weights of all the cats that we now have? Algorithms that require a reduction are not trivially parallelizable because they require that you change the algorithm being used, maybe even waiting on the other parts of the algorithm to finish before you're done. Can you divide the work into independent parts and then assemble those independent parts into a whole? So parallel merge sort is a good example of this. And again, we're sort of running up against the limitations of like my OpenTelemetry hack, but this kind of limited. We don't have a trace for this, but we did, it would look something like Datadog's traces, which do have the ability to do this, where we have those inverted peaks spread vertically with those little lines. Now, if we could sprout 100 arms to pet all of our cats, they'd probably be pretty happy. But in practice, like my brain can barely handle 2 arms, and the density of cats, if there were 100 surrounding me, is gonna be way, way too much to pet. And the point at which competition for resources overwhelms the benefits of parallelism is described by the universal scalability law. And this is the equation, if you're interested, it's the hardest math in the whole thing. And it's the level of parallelism is described by CEN, which is basically linear scaling. The level of contention, which is due to waiting or queuing for shared resources, is alpha. And the level of coherency due to delay for data to become consistent, so like things talking to each other by virtue like the point-to-point exchange, is beta. And the point of showing you that is to show you these 2 pictures. And the first is a picture of Amdahl's law, which is a trace of a single cat receiving a pet. It takes 10 seconds. And the point of this is that once you've optimized a particular operation to its most basic operations, you found the floor of performance. And the second is a picture of a graph of the USL, and the point of that one is to show you the ceiling of performance. Like if you look for this shape in your benchmark numbers, when you start seeing a performance curve like that, then you're running up against the universal scalability law. This one's a little harder to see in like out-of-the-box OpenTelemetry tooling, but benchmarks will help you locate it reliably. Funny thing about the USL is that alpha and beta are experimentally determined, which is how we say in science. So here's our 4 rules. Closer is better, don't wait around. The fastest we can go is the time it takes to do one thing, and doing something with everything is complicated. Now that we know, we can start to guard against future degradation. In most of my example algorithms, I've gone with a recursive implementation because OpenTelemetry is much easier to trace when they're split across multiple methods. It's still relevant to you because in general, if you write a big gnarly iterative algorithm in one particular method, you probably know what you've done. And when it gets sneaky is when you accidentally write a big gnarly iterative algorithm and then scatter it across multiple objects or services. What's worse about this is that you're probably not the only one touching these methods and objects. So simply remembering, hey, don't mess it up, is not really a scalable solution for not borking your performance. What happens when you have a sudden need for 10,000 cats, but someone has added a method to get the total number of beans by iterating through all the key paws? Luckily for us, OpenTelemetry, and particularly Ruby, allow us to point these spans at an in-memory store so we can write code that verifies our performance. And these kinds of performance tests are a lot finer grained than like simple benchmark tests that assert like it's not slower than some particular number. And they're less susceptible to the next developer reasoning that it's only a wafer thin mint and then bumping up the assertion a few milliseconds to make it pass. When we use the OpenTelemetry in-memory span exporter, it creates a list of spans that were exported during the execution of our block. And you can count these spans and make assertions on them, and even check that certain spans, like DB calls, are only called once or not more than you expect. So this assures us, like if we were to have a test like this would assure us that no matter what we do to cat sorts, it will not exceed O(n squared runtime. It doesn't necessarily mean it won't get slower, it just means that it won't get slower at a faster rate. We're still able to parallelize our cat sort, optimize the sequential operations, and do other performance improvements. But now we have a hard upper bound for how fast the time dedicated to sorting our collection of cats can grow. So now we know how to spot performance problems, we know the basic principles of how to fix them, and we know how to keep them fixed. Mission accomplished, we're done. Well, actually there is one more thing. You need to know when to stop improving. It's important that your code be performant, but at some point you're going to run up against physical reality. And at that point, the only real solution is to throw more physical reality and more money at the problem in front of them in the form of faster SSDs, faster processors, more memories. And at this point, you're not running up against the physical reality of performance, but also the fiscal reality of software engineering, which is that the fastest program in the world is worth nothing if people don't use it. And the universal scalability law tells us how much we can parallelize. Amdahl's law tells us how fast we could make it in a perfect world. OpenTelemetry choices show us what we can do to improve our code and help keep it improved. But there's a point at which your program is probably fast enough, and a point at which further performance improvements stop paying dividends. Unfortunately, there's no picture that tells you how fast your program needs to be, and no formula that will know when you've done enough. You're going to have to measure that one for yourself. Now go forth and optimize.